seen the content of our presentation. Now, I'm going to tell you about our project overview. The objective for this paper airplane distance is first to measure and record the flight distance of paper airplanes in meter. Then, we are going to summarize the data using the frequency distribution. After that, we are going to compute key descriptive statistics such as mean and standard deviation. After that, we are going to compare the experimental probabilities derived from the actual flight data with the theoretical probabilities based on uniform model. And lastly, we're going to identify the possible sources of error that may have influenced the result of this project.
Now, I will share with you what is the methodology for this project. The first one, we have number of trials, which are 25 readings. Next, tools and instruments used. We use paper airplane, measuring tape and notebook to record the flight distance of the paper airplane. The third one is the steps on how we implemented this project. Firstly, one of the group member will stand on a fixed line, which is a marker line. Secondly, in a ready position, the student will throw the paper airplane as far as they can. Lastly, another person will measure the flight distance in meters and record it. All these three steps will be repeated until 25 readings are taken. 3 pictures included here show the procedure from step 1 until step 3. On this slide, we have sample space. Each trials give one distance x in meters, where x minimum less than or equal to x, and x is less than or equal to x maximum. For this paper airplane distance experiment, x minimum equal to 1.79 meters and x maximum equal to 4.75 meters. Therefore, S is the set of all x such that 1.79 is less than or equal to x and x is less than or equal to 4.75. Now, let's move to the probability question. The first one, state the sample space in words. So, the answer is the sample space includes all 25 observed length measurements ranging from 1.79 meters to 4.75 meters. For question 2, from your data, find the probability that x is greater than or equal to 1 and less than 1.2, and the probability that x is greater than or equal to 1.2 and less than 1.4. Now, let's take a look on how do we calculate the probability. The formula is number of data values in interval divide with total number of data value. Both intervals have no data value between them. 0 divided with 25, we will get 0 probability for the answer.
So this is the result for our experiment. The shortest distance that we get is at 25 trial, which is 1.79 meter. And the longest distance that we get is at 15 trial, which is 4.75 meter. So this is the result of our experiment in the frequency table. Each range is 0.5 meter. The highest frequency of the distance that we get is from 2.5 meter until 3.49 meter. And the lowest frequency that we get is from 1.5 meter until 1.99 meter. This is the calculation for question 3 and question 4. The question 3, they ask about the probability x more than 1.3 and the answer is 1. This is all because of all of our distance for all trials is more than 1.3 meter and the calculation equals to 25 over 25 trials equals to 1. And question 4, they asked to find the sample mean and the standard deviation. And for answer for the mean is 2.8896 and the standard deviation is 0.6997.
Okay, so for the discussion part, based on the data we collected, most of the distance reading fall between 2 meters and 3.49 meters. There are a few values that are slightly higher or lower, but overall, the measurements are still consistent. Any small differences probably happen because of normal measurements error or maybe slight hand movement during the experiment. So in general, the average distance we recorded is about 2.89 meters. Now, moving on to the questions. For question 5, compute P as less than 1.4 and its complement P as greater than or equal to 1.4. Since all the data from our trials are 1.79 meters or higher, so the probability of getting a value less than 1.4 is 0 because none of our data is below than that. And the probability of getting a value greater than or equal to 1.4 is 1 since all 25 readings meet the condition. For question 6, we want to find the probability of x being at least 1.3 given that x is at least 1. Since every measurement we recorded is already 1.79 meters or more, they automatically satisfy both conditions. So, the conditional probability is going to be 1. Next, for this part of this project, which is calculation of theoretical probability uniform model, I compared the experimental probabilities with the theoretical probabilities that come from the uniform model. First, the theoretical model assumes that all distances between 1.79 meter and 4.75 meter are equally likely. So, the probability density is 0.338. Using this value, we calculated the theoretical probabilities for each range. When I compared this with the experimental results, there were some clear differences. For the range 2 meter to 3 meter, the experimental probability was 0.48, which is higher than the theoretical value of 0.34. This means that, in my actual data, more flights landed in this middle range than what the uniform model expected. So the result was more concentrated around this area. But for distances 3 meter and above, the experimental probability was 0.44, which is lower than the theoretical value of 0.59. This shows that fewer flights travel longer distances compared to what the uniform model predicted. Overall, this tells us that the uniform model doesn't fully match the actual pattern of the data. The real results are not spread evenly. They are more centered and drop off for longer distances.
Okay, on this slide, we are given that the flight distance of a paper airplane follows a probability density function fx equals to kx squared. Our task is to find the value of k and then find the CDF. To find k, we use the fact that the total area under the density function must equals to 1. So we integrate kx squared from 0 to 2. Solving the integrals give us that k is equals to 3 over 8. Now, we use this value of k to find the CDF. The CDF is equals to the integral of the PDF from 0 to x. And we get fx equals to x cubed over 8. And finally, we write the CDF in piecewise form. Now for this slide, we are finding the expected value and the variance of the flight distance. Since we already know the probability density function, which is fx equals to 3 over 8x squared, we use this to compute the mean. Now, we find the expected x. The formula for expected value is as follows. After we solve the integrals, we get 3 over 2 or equals to 1.5. This means the average flight distance is 1.5 meters. Secondly, we find the expected value of x squared. We also need it for the variance. After solving these integrals, we get 12 over 5. And lastly, we need to find the variance. The variance formula is equals to expected x squared minus the value of expected x squared. After substituting the value, 12 over 5 minus 3 over 2 squared, we get 3 over 20 or equals to 0.15. So the variance is 0.15, meaning the distances don't vary too widely from the mean. The first moment is also equals to expected value of x. So by using the formula for expectation, we integrate x times the density. When we evaluate the integral, we get 3 over 2. Then we compute the second moment, which is equals to expected value x squared. This uses the same process, except now we integrate x squared times the density. Solving the integral, we get 12 over 5. And finally, for the moment generating function, which is as shown, we pull out the constant and integrate x squared e to the power of dx. After evaluating the expression from 0 to 2, we get mxt equals to 3 over 8 times e to the power of 2t times 4 over t minus 4 over t squared plus 2 over t cubed and minus 2 over t cubed. So, this slide summarizes the first moment, the second moment, and the final form of the MGF for this probability distribution.
Alright, so to wrap everything up, this slide shows the conclusion of our experiment. Basically, we are summarizing what we discovered after collecting and analyzing the data. The experiment shows that even simple actions like drawing a paper airplane produce results that follow a clear pattern. Using a uniform distribution helps us to see that our theoretical probabilities match the actual distance recorded, proving that probability can accurately predict real-life outcomes. So overall, our result shows that probability really does work in real life, even for something simple like drawing a paper airplane. I think that is all from us, and thank you for watching.